You may have heard that light can act like a particle and like a wave. It can bounce off a mirror like a particle, and it can bend and spread out like a wave. For instance, when it passes through a prism. With careful experiments, we can see how light waves can interfere with each other. But did you know that particles can act as waves too? This is one of the central ideas in quantum mechanics. Everything has a wave nature. Light, particles, and even, in an unobservable way, macroscopic objects like baseballs and people. One way to see the wave nature of light is through diffraction, the way that light bends around the sharp edges of objects or creates patterns when passing through narrow gaps. In the double slit experiment, laser light passes through two slits in a wall and spreads out like a wave as it passes through. The waves coming from each slit interfere with each other, creating a pattern of light and dark spots on a wall on the other side. This happens because when two crests or two troughs of a wave meet, they add together, but when a crest and a trough meet, they cancel out. But what if instead of laser light, you throw particles at the wall? If you have a powerful electron beam, you can see that instead of two spots directly behind the slits, or randomly distributed spots, an interference pattern will appear, just like with the light. The electrons are behaving like waves and interfering with each other. Even weirder, you can slow the experiment down and send one electron at a time. Each electron will pass through and hit the wall at a single point. But over time, you'll see that the same interference pattern appears, even though no other electrons were passing through at the time to create interference. Apparently, each electron is actually interfering with itself. This is the crux of wave-particle duality. Even something we think of as an individual object, like an electron, has an essential wave-like nature and acts as a wave when it's moving through space. The particle nature only appears when it's observed or measured. On the quantum scale, though, for very small particles, that essential waviness fundamentally changes how particles interact with each other, and it means we have to develop new ways to think about and work with the subatomic world. And in some cases, particles acting like waves can change the face of the cosmos itself.
All particles have a wave nature, which is super convenient for me because the particle that I study is super, super small. If you can try to envision how much smaller an electron is than a baseball, my particle is that much smaller than an electron. This means that its wave is huge, enormous, on the size of galaxies. So it's something that would actually be visible. And that's exactly what I study in my simulations of fuzzy dark matter, which is one possible explanation of dark matter, this mystery of missing mass in our universe.
Wave-particle duality applies to everything. If you like, you can even calculate the wavelength of a fastball, but it'll be much smaller than a proton, not nearly enough to blame for a strikeout.